Okay, so we're going to pick up with the second part of Lesson 1 from Unit 5. In the first part, we talked about and looked at this idea of an antiderivative. So today we're going to look at the applications or where derivatives or antiderivatives are useful and can be used. So we're going to start with looking at this evergreen nursery. It says, an evergreen nursery usually sells a certain shrub after 6 years of growth and shaping. The growth rate during these 6 years is approximated by the differential equation d of h dh over dt. That really should have the equals in front of it and not behind it. But the derivative of h with respect to t is equal to 1.5t plus 5, where t is the time in years and h is the height of the shrub in centimeters. And the other piece of information that we're told is that the seedlings are 12 centimeters tall when they are planted at time t equals 0. So there's a couple of things I want us to look at and recognize in this information. It says the growth rate is approximated by this equation. Well, the key word there is rate. And whenever you see the word rate, you know you should think of derivative. So this equation is a derivative. All right, I'm actually going to back up and talk about differential equation. This differential equation, whenever you're told you have a differential equation, that just means that the equation involves a derivative. So, a couple of things there that give you information about what this equation represents. So now let's look at what we want to find first. It says, find the value of the differential equation above when t equals 3. And remember, t equals time. So if we want to simply find the value of this equation above when t equals 3, that just means substitute 3 for t. So I'm going to pull this away and go to clean paper. And this is example, or the A part. And we know that our equation dh over dt is equal to 1.5t plus 5. And we want to evaluate or find the value of this equation when t equals 3. So all we have to do, dh over dt, is equal to 1.5 times 3 plus 5. And then the math should be fairly simple. If you treat 1.5 as 15, 15 times 3 is 45. So that would be 4.5 plus 5, and that equals 9.5. So that's the first part of part A. It simply said, find the value of this differential equation when or at t equals 3. Then it goes on to say, using correct units of measure, explain what this value represents in the context of the problem. This equation, again, represents a derivative. It represents the rate of growth of these shrubs. So this value right here is a rate, and it is, what were our units? Centimeters and years. So our units here are going to be centimeters per year. So what that means is this. At t equals 3 years, the shrubs are growing at a rate of 9.5 centimeters per year. So always think about and process, what does the equation represent? And then when you're describing or explaining what it represents, that helps. The next part, the part B, and hopefully you're following along with your notes, but the part B says to find an equation for h of t, which is going to be the height of the shrubs at any year t. Then the second part says, then determine how tall the shrubs are when they are sold. Okay, so the first thing we've got to do is we've got to figure out what h of t is. Well, if we know that the derivative of h with respect to t is 1.5t plus 5, then to find h, all we have to do is find the antiderivative of both sides of this equation. So, what is the antiderivative of dh over dt? That's simply going to be h of t. And now find the antiderivative of 1.5t. Well, 1.5t, I like to look at that as 3/2 t. So the antiderivative of 3/2 t will be, let's see, the 3/2 times, that'll be t squared divided by 2, which is like multiplying by 1/2. And then, don't forget, the antiderivative of 5 will be 5t. Now, at this point, this is an indefinite integral, so we'll add c. So, what we have now is this. We've got h of t equals 3/4 t squared plus 5t plus c. Okay, well, we need to figure out what c is. And I'm pretty sure we have enough information that we can do that. So let's go back to talking about the height of the seedlings when they are planted. So at t equals 3, not t equals 3, but when t equals 0, we know h of t equals 12. So I can substitute 12 here. And hopefully you're not having to do all of this, but I will substitute my 0. And we ultimately end up with c equals 12. So because c equals 12, our height equation will be h of t equals 3/4 t squared plus 5t plus 12. So there's our height function. And now we want to find, the second part to this question says, then determine how tall the shrubs are when they are sold. Well, if you go back to the original information, it says that shrubs are sold at t equals 6 or 6 years. So if we want to figure out how tall they are when they're sold, then all we have to do is substitute h of 6 or 6 in for t, and I get 3/4 times 6 squared plus 5 times 6 plus 12. Okay, so 6 squared, I'll scoot this up a bit, 6 squared is 36. Then I have 3/4 times 36 plus 30 plus 12. 4 goes into 36 9 times, so that's 27 plus 30 plus 12. That's 57. That'll be 69. And so this value is 69, which represents the height of the shrubs when the shrubs are sold at 6 years. So when the shrubs are sold at t equals 6 years, they are 69 centimeters tall. Okay, so it's very important when you're working through a real world kind of scenario, you have to really think about what information you're given and what that information represents. Okay? All right, so now let's move on to the next example. And we're going to go back to a particle problem. And it says, let me pull that down so we can see it. It says a particle moves along the x-axis at a velocity of v of t equals 1 over the square root of t dt for time greater than 0, t greater than 0. At time t equals 1, its position is 4. Now, aside here. You may think, what the heck is a particle? Well, a particle can be anything, really. It can be a bug, it can be a car, it can be, I don't know. But every time I see the word particle moving along a line, I always think, and maybe you guys have this issue at your house, but I always picture these stink bugs that are so prevalent now in our houses. And I always seem to see a stink bug crawling along the ceiling joist or joint where the ceiling and the wall come in, or where they meet. And so I always see these little stink bugs moving back and forth, typically in one direction, but sometimes they turn around and go a different direction. But so sometimes I see these stupid little, sorry, I shouldn't have said stupid, but these bugs, which are annoying, crawling along the ceiling. Sometimes they turn around and come back this way. And so anyway, this is what I always think of. All right, but anyway, let's get back to the problem at hand. So we've got this particle that's moving along horizontally, the x-axis, with a velocity of v of t equals 1 over square root of t dt for t greater than 0. We know its position, s of 1, equals 4. So if this is the origin, then at 1 second, then the particle is at position 4. So this little sucker has moved 4, or is at 4 at 1 second. Okay, well, and I've put time on there as seconds. I've said seconds, but it's not listed. Anyway, let's move on. Question is, you have to watch the wording, what is the acceleration of the particle when t equals 9? Okay, so I'm going to pull this away, and I'm going to rewrite what the velocity is. V of t equals 1 over the square root of t dt. And part A simply wants us to find the acceleration. Well, what's the relationship of acceleration to velocity? Remember, acceleration is the derivative of velocity. So we need to find the acceleration of this function. Well, for me, velocity is going to be easiest to look at if I write it as t to the negative 1/2 dt. So the derivative of this will be negative 1/2 t to the negative 3/2 power. So there's the acceleration. We want, though, the acceleration of this particle when t equals 9. So now all we have to do is this. 1/2 times, negative 1/2 times 9 to the negative 3/2 power. And without a calculator, that would be negative 1 over 2 times 9 to the positive 3/2 power, which cleans up to be the square root of 9 is 3. 3 cubed is 27, and 27 times 2 is 54. So the acceleration of the particle is negative 1 over 54, and there were no units provided, but that it would be units, let's say it's I don't know, centimeters per second squared, okay? But this is acceleration, so it would be some sort of units squared, per unit squared. Okay, if this were a calculator active question, your answer would be approximately 0.0185, and I'll say centimeters per second squared, even though I didn't include any units. So again, what does this mean? It means that the acceleration of the particle at t equals 9 seconds is -1/54 centimeters per second squared. Okay, so that was the first part. Now the second part to this question, scoot that up a bit. The second part to this question, it says, what is the position of the particle when t equals 9? Well, we started out with velocity, we have acceleration, but we need position. We need x of t or s of t or whatever you want to call the position. So that means we need to think about how do we obtain the position function from either acceleration or velocity. Well, remember that the antiderivative of velocity is position, so x of t will equal the antiderivative of v of t dt, which will equal the antiderivative of, I like the t equals, or not t equals, but t to the -1/2 dt version better. And so the antiderivative here will be t to the add 2 over 2. That's t to the 1/2 divided by 1/2, so multiply by 2. And that is, and we need to add the c, that constant of integration. Okay, so now, what were we told at the beginning about its position? There was a piece of information that we knew that at t equals 1, the position of the particle is 4. And so s of 1, or x of 1 rather, is going to equal 4. So what we can do here is replace x of t with 4, substitute 1 for t, because at time t equals 1, we know its position is 4. So 2 times 1 to the 1/2 plus c, that's going to give us 4 equals 2 plus c, so c is going to equal 2. So the position of the particle can be, for any given time, can be written as x of t equals 2t to the 1/2 power plus c, which we found to be 2. And the ultimate question, though, in part B, was what is the position of the particle at t equals 9? So substituting 9, we get, for t, we get x of 9 equals 2 times 9 to the 1/2 power plus 2. What is 9 to the 1/2 power? That's 3. 3 times 2 is 6, and 6 plus 2 gives us 8. So what does that tell us? That tells us that at t equals 9, the particle is 8 units, because we weren't given any specific units, we'll just say 8 units to the right of the origin. Now, why did I have to include that the particle is 8 units to the right of the origin? Well, I included that because the value of 8 that we found was positive. It was greater than 0, which indicates that the particle will be 8 units to the right of the origin. If this number had turned out to be negative, that would indicate that the particle is to the left of the origin. So here we had this little particle moving horizontally or in the x direction. It could move left, it could move right. If this is the origin, we knew that at t equals 1, it was at position 4. At t equals 9, the particle was at position 8. Okay, so knowing the relationship between a function and its derivative, or you could talk about the relationship between a derivative and its original function or antiderivative, is very useful and important in evaluating and analyzing certain types of information. All right, so our next example, moving on to the next example, I'm going to pull this away for a second. Our next example, we have this. Let me scoot that up just a little bit more. It says, a particle moves in a straight line and has an acceleration that is given by a of t equals 6t plus 4. Its initial velocity is v of 0 equals negative 6 centimeters squared, and its initial displacement, which means position, is s of 0 equals 9 centimeters. Find its position function s of t. Okay, so what are we starting with? We have the acceleration function. We know information about velocity. We also know information about its position. So ultimately we want to find the position. So I'm going to pull this away, or scoot this out of the way. And we will start with what we know. We know that a of t is equal to 6t plus 4, which means at any given time we can determine the acceleration of this particle. So we know that its initial velocity, v of 0, equals negative 6, and we know that its initial position or displacement, s of 0, is equal to 9. So we ultimately want to find the position function. So we need to start with what we know. We know that the acceleration is a of t equals 6t plus 4. So a of t equals 6t plus 4. And if I find the antiderivative, what that gives me, what's the antiderivative of acceleration? That is velocity. So the v of t is the antiderivative of acceleration. Now find the antiderivative of 6t plus 4. And that will be, what, t squared over 2, so that's 3t squared plus 4t plus c. Well, now we have our velocity function that has the constant c, and we'll apply the information that we know about velocity to obtain the value of c. So since time is 0, our velocity at 0, when you substitute 0 here and here, that leaves you with c. So that simply means that c is going to be equal to 6. So my velocity function, v of t, specifically will be 3t squared plus 4t minus 6. All right, now that we want to find, if we want to find position, all I have to do is find the antiderivative of the velocity function. The antiderivative of velocity is position, so s of t equals, the antiderivative here will be, what, t cubed over 3, so that's t cubed plus 2t minus 6t plus c. So the antiderivative of this equation is s of t equals t cubed plus 2t minus 6t plus c. And now I want to take my information that I know about position. Its initial displacement or position is 9. So that simply means that 9 will equal c, because if all three of these are 0, they disappear. So our position function is s of t equals t cubed plus 2t, ooh, that should be 2t squared, 2t squared minus 6t plus 9. And so there is the position function, s of t. So now you can determine, if we needed to, we could find the position of the function at any given time. We could also find the velocity of the, let me rephrase that. We could find the position of the particle at any given time. We could find its velocity at any given time, as well as we could find its acceleration at any given time. So hopefully that is giving us some practice and helping us to get a little bit more comfortable with finding and using antiderivatives. Okay, so let's move on. I'm going to do our next example. This lesson definitely had some quite a few examples, but let me move that out of the way and let's take a look at this. So our next example in our notes says a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff 432 feet above the ground. Several things here. I want us to find its height above the ground t seconds later. This just means find a function to represent the height of the ball at any given time. Then I also want us to find when does the ball, reach its maximum height. So that means we want to find the time when the ball reaches its maximum height. And then we want to find when does the ball, hit the ground. So this particular question, we have several things. Okay, so here's something that we need to bring in and remember. And I've got a little, on my copy it's a little off, but I want to talk about acceleration due to gravity. We've talked about this before, I believe. Acceleration due to gravity is 9.8 meters per second squared, or 32 feet per second squared. And typically both of these numbers are negative, okay? So, and it's because gravity's pull is downward. So acceleration due to gravity is negative 9.8 meters per second squared, and in standard units it would be negative 32 feet per second squared. So to answer these questions, I'm going to pull this away and get to a clean piece of paper here. Okay, acceleration due to gravity. We know that A of t is equal, and I'm going to start out with negative 32 because in the problem it says this ball is thrown with it's thrown upward with a speed of 48 feet per second. So I'm using standard units. So A of t is negative 32. A ball being thrown upward, okay, the speed is 48 feet per second. So we know that V of 0 is going to be 48, and it's being thrown from a cliff 432 feet above the ground. So this talks in terms of height, so I'm going to use h of t or h of 0. The ball is initially 432 feet above the ground. So that's the information that we know. And what we want to find first is h of t. We want to find the height of the ball above the ground at any given time. Well, let's start with what we know. We know that A of t is equal to negative 32. If we want to find velocity, a velocity function, because you have to have a velocity function before you can find a height function, we want to find the antiderivative of both sides. So this is v of t equals, this would be negative 32t plus c. Well, if v of 0 is 48, that means that c is going to be 48. So our v function, our velocity function v of t, will equal negative 32t plus 48. And now that we have our velocity function, let's find our height function. So our height function, we will find the antiderivative of velocity. So this would be h of t equals negative t squared over 2. So that's going to be negative 16t squared plus 48t, and we will add c. And what do we know about its initial height? Well, the initial height at time t equals 0 is going to be 432. So our c value is 432. So our h of t, our height function at any given time t, is going to be negative 16t squared plus 48t plus 432. So there's our height function. That's the A part, or the first part. Now the next question wants us to find when, meaning time, is the ball at its maximum height. So when you see the word maximum, you should immediately think of derivative equals 0. Velocity has to equal 0 when the position is at a maximum. So I know that I have to take v of t and set it equal to 0 for maximum height. So v of t was negative 32t plus 48 equals 0. And when I set that equal to 0 and solve it, this is going to give me 48 divided by 32. That's 1.5. Okay? So just to verify, I'm going to create my little sign chart for the velocity. And if I pick a number less than 1.5, let's say 1. If I plug 1 in for t here, that's going to be negative 32 plus 48. That is a positive value. And then if I pick a number larger than 1.5, let's say 2, negative 32 times 2 is negative 64, which is bigger than 48. So that is negative. So I know from past experience that when the velocity changes from positive to negative, the original function, in this case height, will be at a maximum. So the ball, keyword was when, reaches its maximum height at t equals 1.5 seconds. And then the next question is, so that's the second question. Then the third question is, when does the ball hit the ground? Well, think about the position of the ball when the ball hits the ground. Its position is 0. So we're looking for the time when the position is 0. So I'm going to actually kind of come back up here a little bit. And I need to take my position function, my height function, which is h, and I need to set h of t equal to 0. So that's going to end up being negative 16t squared plus 48t plus 432 set equal to 0. To make my number smaller, I'm going to factor out not just 16 but negative 16, because I'm hoping that maybe I could factor this quadratic if I factor the negative 16 out. That will make the t squared positive minus 3t, and factoring negative 16 out of positive 432, that's going to be a negative, and I'm pretty sure that's 27. Okay, my first thought is yes, I can factor this, but unfortunately I cannot. So I'm going to use the quadratic formula on this quadratic, t squared minus 3t minus 27, and that will give me t equals the opposite of b, which is 3, plus or minus square root of b squared, which is 9, minus 4 times a times c, all over 2 times 1, which is 2, rather, if I get that on there correctly. And when I ultimately calculate that out, the 3 minus this value is going to be a negative number, and I know that time can't be negative, but the 3 plus the square root of this number divided by 2 is going to be 6.908. So what this tells us here is the ball hits the ground at t equals 6.908 seconds. So the ball reaches its maximum height at 1.5 seconds, and it hits the ground at 6.908 seconds. Okay. All right. So I think the next example is very similar to this one. So I'm going to save time and not go through that one in this video. I'll let you work through that. I will say that the answer, I believe, to this question, I'm going to move that out of the way. Our next example is another ball being thrown upward with a velocity of 64 feet per second from an initial height of 80 feet. And we want to find the position function, giving the height as a function of time. Same thing here. And then when does the ball hit the ground? So the ball is going to hit the ground at 5 seconds. And you can kind of work through this. You can check the notes that I've provided, worked out, and, you know, kind of see how you did with that. Our last page of notes goes back to reinforcing and just giving some extra practice finding antiderivatives. There's one thing I do want to point out is that there are some notations for antiderivatives, and I really don't know that these are very important for us to talk about, but an indefinite integral equals an antiderivative. So I'm just going to ignore this right now, and if I need to come back to it, I will. So I'm going to close this particular video out, and as always, if you need anything, please reach out.